Everybody's familiar with nuclear energy, also known as fission, which consists of splitting the atoms to release energy. Fusion is the opposite. In fusion, two smaller elements are smashed into one, releasing energy. The most productive fusion reaction is that of deuterium, a hydrogen atom with 2 neutrons, and tritium, a hydrogen atom with 3 neutrons, to form helium and an extra neutron. This reaction produces more energy from the same massive fuel than a fission reaction does. Furthermore, deuterium and tritium are easy to find or create. It is virtually impossible for a runaway reaction in a fusion reactor, and it produces little to no harmful waste, especially when compared to a modern nuclear reactor. As the nuclei of both deuterium and tritium are positively charged, they naturally repel each other. To overcome this repulsion and allow for fusion, more energy must be added in the form of heat. The fuel for fusion must be heated up to 100 million degrees Celsius. This presents another problem, as at that temperature, the fuel converts into plasma, and no known material can stand up to superheated plasma for long. The solution is to control the plasma with a magnetic field to prevent it from contacting the walls. Currently, the most preeminent fusion reactor project is ITER, the International Thermonuclear Experimental Reactor, that uses a design called a Tokamak. The large amount of neutrons released during fusion bombards the surface of the reactor with high-energy neutrons that degrade the physical structure of the material, as well as cause it to become somewhat radioactive. The material coating the inside of the reactor must be able to stand up to long-term neutron bombardment without majorly deforming, especially if neutrons are to be harnessed for energy production. Also called the blanket, the plasma-facing wall of the reactor protects the superstructure from the harmful effects of neutron bombardment. Furthermore, as the neutrons are slowed in the blanket, their energy is transferred into heat energy, which can then be transferred into a coolant like water for electricity production. Plasma-facing materials must be able to stand up to a high heat flux in neutron bombardment. Yet the largest problem with plasma-facing materials is sputtering. In sputtering, some of the atoms will be ejected, or sputtered, from the wall into the plasma. As these atoms enter the extremely hot plasma, the relative temperature to the plasma cools it. The more cooling from sputtering, the less plasma can participate in fusion, and the less energy can be produced. Here lies a conundrum. Materials with a low atomic number, or low Z, produce less of a cooling effect, but are also more likely to sputter. Furthermore, high Z materials are more able to resist the erosion caused by the high temperature and neutron flux, but cause a greater cooling effect. Current plasma-facing materials in use include beryllium, carbon in the form of graphite, and tungsten. Graphite has been used because of its low Z, high thermal conductivity, and strong bonds. However, due to sputtering, it can form a new molecule with the tritium in the reactor that is then deposited throughout it on hard-to-reach surfaces that would require turning off the reactor to clean and manage. In ITER, beryllium and tungsten are both used. While beryllium has a low Z, it also has a low resistance to sputtering and a low melting point. In ITER, it is not used where the thermal flux is the greatest, and there are fears that a sudden increase in the thermal flux could melt the beryllium. Tungsten is used in the areas of the greatest thermal flux, the divertor, as it has the highest melting point of all metals. However, it has a high Z and thus can cause major cooling via sputtering. Lithium has an even lower Z than beryllium and graphite, making it favorable as a wall-facing material. This would allow for very little cooling due to sputtering. However, the greatest benefit of lithium is that it can absorb the hydrogen and other particles from the plasma. Lithium loves hydrogen, of which the deuterium and tritium used in fusion are isotopes. With hydrogen, lithium can either form lithium hydrides, or the deuterium and tritium can dissolve into the lithium. This all culminates in the form of a liquid lithium coating as the plasma-facing component in a fusion reactor. As the plasma hits the liquid lithium, instead of causing sputtering and ejecting lithium atoms into the plasma, the lithium will soak up the particles. Since this will eventually cause the lithium to become saturated with the hydrogen, a liquid lithium coating is necessary. A coating of liquid lithium will soak up the excess hydrogen as well as various impurities in the plasma such as carbon and oxygen. The hydrogen can then be removed from this lithium and recycled back into the reactor. To have the ability to remove the lithium from the reactor to clean it and recycle the hydrogen, it is necessary to have it flow across the interior of the reactor. However, this can be done using the Lorentz force, which causes the lithium to propel itself using only magnetic fields and electric current, both of which are provided by the fusion process itself. As such, by having a flowing liquid lithium layer as a plasma-facing material, you can constantly cycle lithium and hydrogen fuel in and out of the reactor while ensuring a constant plasma temperature across all the plasma for efficient fusion. While experiments such as the liquid lithium Tokamak experiment have demonstrated the ability for a constant temperature across all the plasma, there are still some issues with lithium. Even though it eliminates sputtering, lithium still faces the challenges posed by the high temperature and neutron bombardment. If the liquid lithium becomes too hot inside the reactor, it could evaporate, which would be detrimental to the whole reactor. In addition, lithium reacts greatly with water. It can combust when reacting with water, but it can also form lithium hydroxide, which is inactive in the fusion reactor and would act as a source of impurities for the plasma. Lithium has already shown great promise toward improving the plasma stability of a fusion reactor and is already vital for breeding the tritium used as fuel. Regardless, there is no doubt that lithium will play a large role in making fusion and near-limitless energy a real possibility in the near future.